Okay, constant operands. Any of these suffixes that we've been, so let's go back to an example. Let's say we have add 5 to EAX. Okay, anytime I use an immediate value, it can be coded any different way. I can do it this way. I could say instead of 5, this assumes decimal because I haven't indicated by putting any little character behind it that it's another base number. I could also say for the same thing, 0101 B for binary, 05 hex. I could also say 05 Q or a lowercase o, but that is so hard to read or in particular differentiate between that and a 0 that when people use octal, they pretty much indicate it by a Q. So for us, it's not really an issue because we don't use octal much. We won't in this class. Most of the time, again, because that's what you'll see in a debugger, most of the time we're going to use hex. All right, here we have, this is actually an instruction. It's not an instruction. Well, it is an allocation of memory. We would see this particular line in the data segment because this is a directive that allocates 1 byte of memory to a place in memory associated with this identifier. So in this case, I have indicated the initial value, but again, I could also indicate the initial value, and instead of saying this, I could say 7D, I could say 125, which would be decimal. I could also say, 175 octal. So you get the idea that we can indicate constant operands in many different ways. When we're reserving storage, I've talked about it before, but we can, let's say, mask I'm just copying our instruction from the last one. Byte 125 is our initial value. That allocates 1 byte of memory. I could say word. That's another directive that allocates 2 bytes. I could say D word. I could say Q word for quad word. Okay? All right. So, more examples. This first one allocates a byte of memory. Whoops. This first one allocates a byte of memory and gives it the identifier string 1, initializes it this way. I could also, if you look in the ASCII table, I could do it the same thing that way. This third one, actually allocates memory for an array of byte-size characters in memory and initializes it to these characters. So if I looked at the piece of memory called string, I would see these hex characters, 68, 65, 6C, 6C, 6F, H. So that's what I would see as the initialization in memory if I were to look directly at memory. Okay, be careful. I think I've mentioned this before and we'll definitely mention it over and over again. The machine, there can be no ambiguity in the size of the operation. So as a machine is going to take an instruction like, we'll go back to our old standby, and it's going to look first at the destination operand. The destination operand is going to be the first thing it looks at to determine size. If it doesn't see it there, it'll then look at the source. In this case, our destination is a 32-bit register, so this is a 32-bit addition. In this case, I've got a problem because I've allocated 1 byte of memory for this identifier, but I'm trying to move this 8-bit value to a 16-bit register. This will give you an error. You'll get, it says something like size mismatch is what it says. So just be careful on that. Again, we'll mention it many, many times. All right. So we've talked about opcodes, or at least instruction formats as far as opcodes are concerned. When we talk about operands, there are 3 different types of instruction operands. There are constants or immediate values. So this could be 100, for example, or null, or 0 if I want to say null something. Constant or immediate, I could have something in a CPU register. This is the case when well, let me just write this. And then I can also reference memory locations. So for this last one, an example might be, let's add ECX to sum, or EAX to sum. For these other two, an example that would represent both of them is the one we've been using, where my source operand is an immediate value, my destination operand is a register. Okay, so those are the 3 basic types of instruction operands. So let's talk about the addressing modes that go with each of those. So there are 3 general addressing modes used with this family: immediate, register, and memory. In immediate, the data is located in the instruction itself. So going back to our previous example where we said we're adding 5 to EAX. 5 is immediate value. It's not a value stored in a register or a place in memory. Therefore, since it doesn't have a place where it's stored, I have to store this immediate value with the instruction itself. In the case of register, the data is located in a register. Okay? In the case of memory, data is located at some address in memory, and here we have to indicate a little bit further how we're addressing memory. So there are 2 ways of addressing memory. One is direct, and let's just do this. Direct and register indirect. Okay, so our example, same one. In this case, my destination is a direct memory address, so I'm using an identifier. In this case, I am indirectly referencing memory using a register as a pointer. So with direct, an operand indirect mode has a 32-bit address for a memory location built into the instruction. So I would have to look for the address of sum as part of the instruction. Okay? Register indirect uses the address in the register to locate the contents in memory to be used instead of using the data stored in the register directly. So again, as we go through this, we'll pay more attention. Specifically, when you tell me the addressing mode for memory, you must say either direct or register indirect. Do not just say memory. You've got to be a little more specific than that. Okay, so let's play with this just a little bit. We'll do an example. So in this case, I want to add what EBX is pointing at to what is in EAX. Okay, so EBX is right here. This is because I look at my destination, it's a 32-bit addition, so I'm going to look at the 32 bits stored at where EBX is pointing, so it points to that. Let's do the addition. So I've got OC31 FC92. Now here, we have to remember that we're reading this as a multi-byte scalar value that's been stored in memory. So when I pull this out, I'm actually going to say, I'm adding 7290E310. We do the addition. 2A 12 plus 3 is 15. 15 plus 14 is D, carry my 1. I'm going a little bit fast, I apologize. So here is my answer. That answer is going to be stored in the destination. So EAX after is going to be, oh, let's see if I can write this a little bit smaller. 7E C2 D F A2. Okay, and that's actually going to overwrite in memory. Now again, we're overwriting, so this is a multi-byte scalar value that we're about to put in memory. It's going to go in reverse byte order, which means the least significant byte will go in the lowest address. So here is how this will look in memory. C2 70. So let's modify this just a little bit. Now you'll notice that this is not a 32-bit addition, but a 16-bit addition. In this case, I'm going to be adding what is in AX. Well, this is in AX, so FC92 to the 16 bits that EBX is pointing at. So I'm just going to be looking at this. So plus E310. Do the addition to a FD. That is the only part of EAX that will change. So EAX after is going to be 0C31DFA2. That's the only thing that we see changed. Here, I am overwriting, well, I've just seen that. So, does that make sense? Hope so. One more example, and then we'll call it a video for this one. In this case, what's going to happen here? I'm going to get an error message. Why? Because there is a size ambiguity. Remember, I am the processor. I look first at the destination. Well, this is a pointer, so I don't know, am I pointing to a byte? Am I pointing to a word? Am I pointing to a double word? I don't know. So I look at the source operand. The source is an immediate value that could be either a byte, a word, or a double word. So I'm going to get a size ambiguity error. Neither operand indicates the size of the operation. So here's the deal. Even if your IDE lets you get away with this, realize that you would this would normally result in an error, so you're going to lose some points. All right, let's call it a video with that one. We've got a few more things to do, but that's good for now.